An experiment consists of multiple throws of a fair die. We saw in the simulation of a fair die in the last video that each outcome, each number that is, has relative frequency approaching 1 over 6. Let U be the set of all equiprobable outcomes of a throw. A throw is one trial of our experiment. So I've drawn a rectangle to represent U. You might be familiar with this. The letter U is often used for a universal set. So these are all the outcomes of a particular trial, and they're equiprobable. They all have the same probability. Each of them has a probability of 1/6. An event is a subset of U. So we call our general event E. Here's the set notation for a subset. E can be a subset, or it can actually equal U. So for example, the number 1 is a subset of U. So each of these 6 equiprobable outcomes is an event. Each of them consists of just one element, and it's a subset of U. And we can make any subset of U, of course. We can combine these two outcomes together, and this is a subset of U, so this is an event. In this case, the event would be getting a 2 or getting a 5 on the throw of a die. Or you could imagine an event consisting of these numbers here. This event will be the event of getting a 5 or 6 on a trial, or a single throw of a die. The probability of an event is the number of elements in the event divided by the number of elements in U. Let's look at an example. Here is an example that we did in the previous video. So, in the same die throwing experiment, we're letting E equal the set consisting of the elements 2, 4, and 6. We can see that E is obviously a subset of U. To find the probability of E, we take the number of elements in E, which is 3, 1, 2, 3 elements in E, and divide it by the number of elements in U. Well, the number of elements in U is 6, so we get a half. We did this example in the previous video. Well, we looked at the relative frequencies of getting a 2, a 4, or a 6, and we added those relative frequencies together. And we found that the sum approached a half as we took more and more trials or throws of our die. We could, of course, indicate the subset E on our diagram. We could just section out those elements of U which are even numbers. So we could just draw around the even values. And here is our set E. So we're just looking at the fraction of the set U which is taken up by the elements of E. And that fraction is a half. Half the elements of U gives us the number of elements in E. Let's look at an example involving mutually exclusive events. We touched on this in the previous video, but now I'm going to look at it in the context of set theory. So we're going to find the probability of getting a 1 or an even number. What I will do is I will call the event getting a 1 H. We use capital letters for events normally. And I will use capital E to stand for the event of getting an even number. So E has outcomes 2, 4, or 6. Let's look at these sets in the universal set. We could put a circle around 2, 4, and 6. I'm just going to rearrange these elements to make it easier to read. So I'll put a circle around 1 to represent the set H, and I'll circle these. This set is E. We can see that obviously both H and D are subsets of U. We note that sets H and E are disjoint. Disjoint means that they have no elements in common. Or we could say that the intersection of H and E, H intersecting E, is empty. This symbol represents the empty set. Now we're interested in the probability of the events H or E. The event H or E is H union with E. So we get the union of these two sets. So we just follow this rule here. Probability of an event is the number of elements in the event divided by the number of elements in U. So if we want the probability of H union with E, we want the number of elements in the set H union with E divided by the number of elements in U. Well, let's write out the set H union with E. I'll just write it over here. It's 1, 2, 4, 6. We just put these elements together. So we can see that there are 4 elements in H union with E, and of course we have 6 elements in the universal set. So our answer is 2/3. So we can see quite clearly from our set that 2/3 of the elements of U consists of the elements of H and E. So the key thing to remember here is when we're getting the probability of one event or another event, we must get the union of the two events. We can see that if the outcome of a trial is event H, then that outcome cannot be E. So event H occurring excludes event E occurring. And similarly, if the outcome of a trial is event E, that means that a 2 or a 4 or a 6 appears on a die, then this event excludes event H. So we can see that H and E are mutually exclusive. Now let's look at the OR rule and an example of non-mutually exclusive events. So, like in the previous examples, an unbiased die is thrown. Find the probability of getting an odd number or a number greater than 4. So I will let capital O stand for the event of getting an odd number. So to get an odd number, we need to get one of the outcomes, 1, 3, or 5. I will let capital G stand for the event getting a number greater than 4. So as a set, G must consist of the elements 5 or 6, because 5 and 6 are greater than 4. Now we're getting the probability of one event or another event. So the rule is we get the probability of the union of the two events. First of all, let's write out the union of the sets O and G. So we just write out the elements that are in both sets. So we have 1, 3, 5 from set O, and from set G we have 5 and 6. Now we do not write down the 5 because each element must appear only once in a set. So we just write down the element 6 from set G. So we can see here that these two sets are not disjoint. They do have elements in common. If we take the intersection of set O with set G, we get the set consisting of the single element, which is 5. Anyway, the probability of O union with G is the number of elements in O union with G. So we're just following our rule, and we divide that by the number of elements in U. So we have 1, 2, 3, 4 elements in O union with G, and we know we have 6 elements in U, so we get 2/3. We can see here that events O and G are not mutually exclusive. If event O occurs, so if an outcome of a trial is event O. That means either a 1, a 3, or a 5 appears on the die. Then it does not exclude the possibility that event G has occurred. Because if 5 appears, then event O has occurred, but event G has also occurred. So if event O occurs, it does not exclude event G occurring, and vice versa. If event G occurs, so in an outcome of a trial, if we get a 5, event G has occurred, but event O has also occurred. So events O and G do not exclude each other. Let's look at the probabilities of events O and G separately. The probability of event O is the number of elements in O, which is 3, divided by the number of elements in the universal set, which is 6. So we get a half. The probability of event G is the number of elements in G, which is 2, divided by the number of elements in U, which is 6. That gives us 1/3. Now we know that if we take O union with G, well, let's look at the number of elements in O union with G. It's equal to the number of elements in set O, which as we can see is 3, plus the number of elements in set G, which as we can see is 2, minus the number of elements in the intersection. We know that we have 4 elements in O union with G. There are 3 here, 2 here, but 3 plus 2 is 5, so we have 1 element too many. See, the intersection has been counted twice. If we just add the number of elements in O and G together, we're counting the intersection twice. If the sets are disjoint, if there is no intersection, then we just have that the number of elements in O union with G is the number of elements in O plus the number of elements in G. However, we see that we do have an intersection, and it's counted twice, so we have to subtract it off once. Now let's divide this equation by the number of elements in U. Now, we know from earlier that this thing here is just the probability of the event O union with G. And here we have the probability of O. The next term is the probability of G. And the last term is the probability of O intersecting G. Of course, if O and G are mutually exclusive events, that means that the intersection of O and G is empty. There are no elements in it, so this term won't appear. The probability is 0 because the number of elements is 0. Then the probability of O union with G is the sum of the probabilities of O and G. I'll go to the last example where H and E were disjoint events. H was the event getting a 1 on the throw of a die, and E was the event getting an even number. And if we want to get the probability of H union with E, we can follow this rule here, but we see that the intersection of H and E is empty. We saw that earlier. So we just have to sum the probabilities of H and E. What's the probability of getting a 1 on the throw of a die? Well, that's 1/6. What's the probability of getting an even number? Well, that's 3/6. 1/6 plus 3/6 is 4/6, which is 2/3, as we saw before.